let me show you guys this real fast so we all know where it's at. So real quick, I want to show you guys where I've placed the homework tonight. And it'll probably be like this for the next couple of days here and there. The one disadvantage of the Pearson text that we're starting with today is that it doesn't have the style problem that I'm hoping that you guys are going to work towards. So what I've done is I have a tab up here that says Old Algebra 2 book. I'm sure you might see it. And what I've done is I have one of two things. Do me a favor real quick. If you guys click this link, does it open to the old site? Does it link out okay? Did everything that show up? All right, cool. Just wanted to make sure that that still works, that hyperlink is working. This is the site that I used last year. I'm not putting anything new on it or anything like that. So let's go back to the old text real quick, back to here. I placed the actual PDF file of what I want us to work on tonight here. So you should be able to also just click on this and it'll pop out in its own screen. Did that happen for you guys?
Yeah.
I just wanted to make sure it did that. This is the stuff we're talking about today. It's actually, it happens to coincide with the exact same section, which is kind of nice, but it's called linear programming. And let me show you how this stuff is going to work. You'll also see, I wrote down do problems, whatever. I wrote it on here for you, so the assignment's already there. But let's go back and just kind of make sure we all know how to do this then. Linear programming. Linear programming is one of the ways that we learn how to create what's called a feasible region. This feasible region comes from specific what are called constraints. Yesterday and the day before and all that stuff, you guys have been graphing systems of systems of inequalities. We've done a little bit of graphing of the absolute values with the inequalities as well. We've also done solving systems of equations when we would find the intersection of 2 points via whether it was a linear combination turned into an elimination method, or whether or not we just went ahead and just used straight substitution. What this is going to allow us to be able to do is to take specific values from eventually a word problem to create a region of test points. These test points are going to be the intersection of multiple lines. And those test points, the ordered pairs, we will eventually substitute into what's called a maximum or a minimum. We want to find a maximum or a minimum value with a specific cost function, we'll just call it. Okay? You're trying to get, these are the ways we're able to get the biggest bang for our buck, if you will. So we're going to look at today some very quick constraint stuff. And I don't want to use graph paper at all. It is so much easier to do this style problem when we freehand it. And what we need to be able to do is understand where the problem is going to occur before we draw graphs. So in this case, this is one of the benefits of the older textbook versus the new one. The new textbook puts these values last. The old textbook put them first. I like to use these first because it tells me where to locate these, as opposed to locating and then figuring out where they should be. So, and I remember like in Flex last hour I was saying, hey, do this one first because it's easier. That's the reason. Believe it or not, I have half a clue. It's hard for you to believe that, I know. So if I'm looking at x is greater than equal to 0, y is greater than equal to 0, where does that occur? Remember yesterday we talked about quadrants? It's at the origin and it goes to what quadrant? Quadrant 1. It's the first quadrant problem. So what I would do is draw first quadrant. I know that all of my x values being greater than or equal to 0 move this direction. And I know all my y values being greater than or equal to 0 move upward. So again, I'm just going to draw a couple arrows. Notice I'm not shading. I'm pointing direction. It's going to be cleaner. And now I have a whole bunch of inequalities that I'm just going to do cover and solve. I'm going to solve them via their intercepts. Okay? So if I take and I cover x and I solve that equation for y, where's my y-intercept? 5. The ordered pair would be at 0 and 5. Where's the x-intercept? Negative 15. Now, right now, I'm looking for this quadrant, but since my intercept is back this way, I'm just going to do this real quick and put a dot at negative 15 and 0. I know it's not going to have anything to do with the problem, but now I can at least see what direction the line is moving. It's going there. Are we okay with that? Now I have to go back to the original problem, and I have to figure out what direction to shade. And what am I going to use for my shading purposes? The origin. Yeah, very good. 0, 0. So what's 0 plus 0? 0. Is 0 smaller than 15? Yes. So I'm going to shade this direction. Again, notice, I'm just pointing arrows. And I've already gotten rid of all of this stuff up top. I'm just wedging it into here as of right now. So far, so good? Okay. What's that?
I said it always makes sense in class. It never makes sense here by yourself.
That's why I record all this.
Yeah, I know.
So you can rewind it. Where's your x-intercept? And your y-intercept? Put some dots. Ah, that looks good for a 6. And this looks good for a 12. Ish. Exactly. And as you do a couple of these, believe me, the first few you do, you're going to be your scale. You'll be like, wait, that doesn't make any sense. And then you'll realize, oh, maybe I should have moved this over a little bit further. And I'd say by Wednesday, this is nothing. Okay. So now I have to check it again. What's 0 plus 0?
0.
Is 0 smaller than 12?
Yeah, sure.
So again, it's moving inward, so it's coming back this way. So we have this region in here, and I don't want you guys to shade that. I'm just showing you where it winds up. We know 1, 2, 3, 4 points of intersection, with this one being at 0, 0. But where's this one? How can you find that? System of equations. When two lines intersect, it's where you the solution set for the system of equations. So in this case here, what I would do then is go back to what we did a couple of days ago, and I'm going to solve for where those two lines intersect. I'm going to use the systems of equations again. Now, when I do that, I really don't care about inequality. I treat it just like a regular equals for both of them, because you're solving for where those two run into each other, so you're just looking for that specific point. You're not trying to shade anything, you're not trying to do anything like that. You're just trying to find that point of intersection. That's it. Okay. So I'm looking at this. I have negative x plus 3y to 15, a 2x, a y, to 12. To me, in my mind, I think that the easiest and fastest way to solve that system of equations is to double the first equation and then add it to the bottom one. Does that make sense? Because then I can eliminate my x values real fast. So, double this one. I get negative 2x, a 6y, and a 30. And I'm going to add these together. Very good. 7y is 42. And y is 6. You okay with that? So I know the y value here is at something 6. So I'll take this value of 6 and go right back to here. 2 times what plus 6 is 12. 3. Pretty quick, isn't it? So the ordered pair at which these two intercepted each other is at 3, 6. Now I have all 4 points of intersection that eventually I'm going to be looking for. So the idea is we're taking what we did with the system of equations, we're taking the shading values of inequalities, and then we're creating feasible regions to do cost analysis with. Math! Thank you. Thank you. I'll be here all week. Well, at least until 2:50. Get it? This isn't bad, is it? Good question. The 4 points that we're looking at here are the 4 points of intersection that are contained by the region. Does that make sense? Yeah, a lot of them will usually be on axes, and then where intersections occur. And this is a great question. This region is completely bounded. It's completely bounded. It's enclosed. I forget what that's called. Sometimes you can get a region that has it might just open up to the bottom and the bottom might fall out. There could be a trap door. Okay? It might not have a base. It might be an infinite minimum. Same idea. We could have an infinite maximum. Swings, it looks just fine. Let's do another one. Let's do another one in terms of finding a maximum. Now, to start with today, this maximum equation that we're going to try to find the maximum of will be given to you. Eventually, you will be getting in reading problems that sound like this. Find you where they are. Yes, sir. Well, you're going to learn to love them real fast. You'd be surprised at how awful they start out with, but then people go, oh, that's really easy. Let's go back to proofs. I'll read it to you guys. So we have some constraints. We have x is greater than 2, x is less than 5, greater than or equal to, less than or equal to 5, y is greater than or equal to 0, and then I have a linear equation then as well. So in this case, I'm not being bound just singular first quadrant. I could have some other stuff going on. So what I don't have, whenever I don't have x is greater than or equal to 0, y is greater than or equal to 0, I'm going to just put that in because I know it has to be within the first quadrant, but I'm going to narrow it down a little bit further because they gave me these two parameters. So anytime you see x is equal to a number, what direction is the line moving? X equals a number are always vertical lines. Okay? So if x equals a number, so x is greater than or equal to 2, well here's 2. 2, 0, and it's greater than or equal to that, which means it's going to the right. You be okay with that? Sure. X is less than or equal to 5, same thing, it's a vertical line through 5. Then which way is this pointing? Yep, it's going back to the left. My next bit of information says that y is greater than or equal to 0, which means it's everything from 0 up. So I don't care about these parts down here anymore, but I know I'm going this way. So right now I have an open box. I have a 3-sided box. It's tabbed upward. That last equation is what's going to allow us to put a lid on it. Now, we could graph this because it's in slope-intercept form, but then you have to walk your slope and do all other junk. Can you put it back into standard form real fast and do a quick graph? move the negative 2x back to the left, and you get 2x plus y is less or equal to 12. And now you can do a quick graph faster. Because you can get your x and your y intercepts back. Where's your x intercept?
6.
Where's your y intercept?
12.
There's a 6. There's 12. What's 0 plus 0?
0.
Is 0 smaller than 12? And I'm moving inward then. No, I moved it back to the left, so I added the 2x over. Good question. So do you guys all see where you have 4 points of intersection again? We're here, 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 here. What's nice about the vertical line parts is that you know the x-coordinate for both those other parts on the slant. You know that the x-coordinate here, since this is 2, it has to be 2 up here. If this is a 5, this has to be a 5 here. How do you figure out what y is? Welcome, Sean. Very good. Welcome. 2 times 2 is what?
4.
4 plus what is 12?
3.
2 times 5 is what? 10 plus what is 12?
2.
Oh, look how fast math can work. You'll be surprised. It's not that bad. Okay. So now we've used quick graphs, so we'll just move that. And we have 4 ordered pairs that we're going to check to see which one of them gives us the maximum value at that constraint function. So we just write them down. We are at 2 and 0, 5 and 0. Oh, does it matter the order in which you labeled your, when you write down your 4 or 5, whatever intersection points there are? Makes no difference. Right. We're trying to figure out which one of these ordered pairs is going to allow us to get the maximum value. When I read you guys a word problem, you'll see how the maximums come into play. So what I'm doing now is just substituting in 2 and 0 to our constraint function. Negative 2 plus 3 times 0. Negative 5 plus 3 times 0. Negative 5 plus 3 times 2. And negative 2 plus 3 times 8. Our 4 separate values then become negative 2, negative 5, 1, and 22. Which one of those gives you a maximum?
22.
At 2, 8, you get a maximum. At which of those values would it give you a minimum?
5, 0.
At 5, 0. And that's what this stuff winds up looking like. Now, like I said, these word problems as we get to them, they're going to sound like this. An office manager is purchasing file cabinets and wants to maximize storage space. What do they want to maximize?
Storage space.
So you want to find the maximum storage kind of idea here. An office has 60 square feet of floor space for the cabinets and $600 to purchase them. You're bound then by floor space and money, which means the equations will deal with money and area, surface area. One cabinet requires 3 square feet of floor space and has a storage capacity of 12 cubic feet and costs $75. The other one is 6 square feet of floor space, storage capacity of 18 cubic feet, and costs $50. How many of each of them should you buy to maximize your storage capacity? That's the kind of stuff you're able to develop into your own words. Yeah. Well, remember, this textbook is from 1990. 6, somewhere around there? We will. We'll start with that. We'll start the word problem baby steps on Tuesday. Okay. I am going to unfortunately break my streak of not giving you guys any handouts. Sorry, I killed a small shrubbery to run off a couple of pieces of paper for you. I will give them to you on Tuesday. I find that when we're dealing with this style linear programming problem, it is usually a little bit easier to have them in front of you on paper. And I did this when we had the textbooks also. That way you can make markings on it and you can see exactly what you're working with. So let's do another one real quick. Why don't you guys take a minute and see if you can do this one on your own. Find the maximum value with the following constraints. So I want you to create your own bounded region, find your ordered pairs, and see which one gives you the maximum. Well, we'll do max and min, doesn't take that long. And then we'll check it, and then I'll give you guys, well, you guys already have the homework, so. We're okay, oops, sorry. We're okay that it is a first quadrant problem. X and Y intercepts of 5 to start. All right. We know that is 0 plus 0 bigger than 5? No. So I know right now I'm moving outward in all of this. Okay. The next one has intercepts at what is that? 4.5 and 6. 4.5 is a little below it. And I'm going this way. Also false at 0, 0, so it's moving upward. Now, I saw how you guys were shading that it's overlapping in these two little, like the bow tie region, if you will. But the pure overlap becomes outside of it, and there's one intersection point here. So it's the region that is bounded like this. So it looks like that-ish. Now, the only point we have, will this region have a maximum value? No, it won't, because is there a lid on it? There's no lid, so there's no maximum value. We can find a minimum value, but there is no maximum value because there's no lid.
What do you mean by lid?
There's no boundary here to stop it.
Oh, okay,
Does that make sense?
yeah.
Yes, ma'am.
What exactly is C?
There's constraint function, cost function. That's all it stands for. It doesn't stand for anything else.
So like what if you asked us maximum value on a test which there wasn't a maximum value?
You would write no maximum value.
Okay, so it would be like a
Unbounded region. It wouldn't be 0. It just say no maximum value.
okay.
Now I still can figure out the intersection point here, and the way I would do that, I would use substitution. I'd say that x is 5 minus y, and I'd substitute into here and go for it. But I just wanted to show you guys that sometimes you can get a no maximum value. Bless you. We okay then?
Yes.
Do I have to go through the ordered pair there, or we can do that, right?
So there's 5.
I'm sorry, what's that?
5.
5 what? No. Your only intersection points that where the overlap is the 6, 0, where it hits here, where these two lines intersected, and where it hits here. There's only 3. Because this boundary is stopped here, and it does not change spot after it goes that. So as it's coming, it's dropping down, it changes direction here, changes direction here, here, and goes on. There's only 3 spots to worry about.
How do you know which ones to use for like the intersection that we don't have? Because you have this for before the.
What'll happen when you start messing around with when you start graphing these, you'll have to remember which line was this equation, which line was that equation, and just figure out the solution between the two.
Oh.
Does that make sense? You're looking at where they're running into each other. You just have to pay attention where you got it from.
How do you figure out the intersection for the 1 and 0?
For what one? I would use substitution like this. I would say x is equal to 5 minus y, so 3, 5 minus y plus 4y is 18. 15 minus 3y plus 4y is 18. Y is 3. X is then 2. That's all I'm doing. I would use substitution because it's quicker than doing linear combinations. I just skipped the step because I didn't want to do it. Do your homework. You got it on the assignment already. It's on, I posted it right there on the website itself, and then it's on the calendar. So again, if you had forgotten where it was, regular old website, old Algebra 2 book, it's there tonight. And it pops up, it says, do these problems. It's 12 through 20 evens, okay?